Imagine a system processing millions of data points a second. Financial transactions, server telemetry, sensor readings. Data that arrives unpredictably and never stops. The engineering challenge here is precise, identifying and maintaining the exact kth largest element from this infinite stream, and keeping it available for retrieval at any given millisecond. The standard instinct is to simply append every new piece of data to an array and resort the entire list. This chart visualizes the flaw. Applying an n log n sorting algorithm to an endlessly growing dataset creates a computational bottleneck. With every new element, sorting takes longer. Latency compounds, starving the CPU until the architecture collapses under its own operations. Processing a static dataset is a solved problem. Infinite data streams require architectures that strictly decouple processing time from the total volume of data passing through the system. When tasked with finding the largest items in a dataset, the immediate professional reflex is often to reach for a max heap data structure. By definition, a max heap organizes itself so that the absolute maximum value always sits at the root, making retrieving the largest item instantaneous. But to find the 10th largest, you have to pop the root 9 times to expose it. This strips away the top of the tree, destroying the heap state, rendering it useless for the continuous stream. Counterintuitively, the optimal way to track the kth largest element requires a min heap. We construct a min heap, treating it as a gatekeeper bounded to exactly k elements. By only allowing the k largest elements seen so far inside the structure, the absolute smallest of this elite group naturally rests right at the root. This inverts the logic. Instead of maintaining a descending sorted list that grows forever, the min heap maintains a constantly accessible threshold point. JavaScript lacks a built-in priority queue, requiring us to engineer this custom structure from scratch. Looking at the min heap constructor, we initialize a simple flat array, rather than a complex network of distinct node objects. We map a binary tree onto this flat array, using straightforward index math. To find the left child of any node at index I, the formula is simply 2 times I plus 1. The root is at index 0. Its left child lives at index 1. The formula for the right child is 2 times I plus 2, placing it at index 2. This cascades perfectly. Index 1's children are at 3 and 4, mapping the entire tree geometry without any physical node links. Traversing back up uses the inverse calculation. To locate any node's parent, you subtract 1 from the index and divide by 2, rounding down. Imposing this implicit mathematical hierarchy over a flat array eliminates object allocation overhead and packs the data tightly together to maximize memory locality. When we call the push method, the first step is to blindly append the new data to the end of the array. Visually, this places the new value at the very bottom right of our implicit tree structure. This placement risks violating the core min heap invariant. Every parent must be smaller than its children. To correct this, we trigger the bubble up method. The method enters a while loop, executing that parent calculation to check the new element against the node directly above it. If the new child is smaller than its parent, JavaScript's destructuring syntax swaps their positions. The element iteratively swaps its way up the tree, stopping only when it encounters a smaller parent or hits the root. Because this insertion only traverses a single vertical branch, its computational cost is bounded entirely by the tree's height, ignoring the array's total length. Extracting the minimum value carries structural risk. You can't just delete index 0, because shifting the remaining array elements over by 1 would break the entire index math mapping. Instead, the pop method stores the root value, pops the absolute last element off the end of the array, and uses it to manually overwrite index 0. This preserves the array geometry, but it places a heavy leaf element right at the top, immediately violating the heap invariant. We restore mathematical order by executing sync down. The algorithm calculates the positions of both the left and right children for the current node. It runs conditional logic to identify the absolute smallest value out of the parent and those 2 children. The heavy parent then swaps places with whichever child is the smallest. This loop forces the heavy element to sink down branch by branch until it is smaller than any remaining children below it. Ultimately, state restoration is efficiently achieved through targeted vertical displacement, rather than expensive full horizontal array resorting. With the internal mechanics verified, we move up the hierarchy to the kth largest wrapper class that controls the min heap. The constructor initializes the heap and immediately processes the initial numbers array directly through the class's add method. Phase 1 of the add method simply pushes new values into the structure until the heap size reaches exactly k. At this exact moment, the structure is capped. Phase 2 evaluates each subsequent element against the root threshold. An incoming value is checked via the peak method. If smaller, it fails and bounces off. If larger, it triggers a pop, discarding the outdated root, and a push, inserting the new value. The class acts as an algorithmic sieve. It instantaneously sheds irrelevant data and devotes processing cycles strictly to elite values. This sieve logic dictates the final efficiency of the system, neatly expressed in big O notation. This diagram isolates our structure. The physical memory footprint is strictly capped. Because the heap physically rejects any elements beyond size k, the space complexity remains a perfect O of k, even if the stream eventually processes 10 billion elements. For time complexity, reading the root is a constant O of 1 operation, but when data actually passes the threshold, it triggers an insertion. Because the tree is capped at pay nodes, traversal during a push or pop operation is strictly limited by the height of the tree, giving us a highly efficient insertion time of O of log k. True scalability in streaming architectures is achieved by strictly bounding state, transforming infinite data problems into controlled, constant space operations.